determine the convergence of the series. If the series is alternating, state whether it converges absolutely or conditionally. Alright, so you have this alternating series in this case, the very first question. If you take the non-alternating part, so if we get rid of the negative 1 to the nth power, this is what we have. And you should really know some concepts about which one goes faster. So if you compare a log with a regular polynomial, then logs increase much slower. An example of this would be like if you have log base 10 of 1000, that's only 3. So logarithms produce much smaller numbers than regular n, and therefore when you have n over log of n plus 1, the top will increase faster rather than the bottom. Okay? So that means this is going to go to infinity, and if that's going to infinity, then this won't converge at all. Now, how would you show that this actually goes to infinity? In that case, we will need to use the L'Hopital. So we say limit n going to infinity of n over log of n plus 1. When n is infinity, they both give you infinity, although the bottom one increases infinity much slowly. It still managed to be infinity over infinity, which means we can use L'Hopital. So if we differentiate n, we get 1. If we differentiate log of n plus 1 by the chain rule, we can say it's 1 over n plus 1 because log differentiates to 1 over x, which gives you limit n going to infinity of n plus 1, which is infinity. Right? So that means limit n going to infinity of negative 1 to the nth included is not going to any fixed number, and this will make the sign alternate, so it's going to be like positive infinity, negative infinity, and alternating those two when n is really large. So that's going to be just simply does not exist. That means by test for divergence, which is also called the nth term test. By the nth term test, we have this series diverges. Okay, next one. We have 1 over n squared minus 2 over n factorial. Now, we know that 1 over n squared converges because it's a p-series with 2. And 1 over 2 to the n also converges because if you think about this, this is like 1 over 2 to the nth power. So it's a geometric series. So adding these will give you a finite number because this r is 1/2. Which is between 1 and negative 1. Now, if you had a hard time figuring out that this is a geometric series, you can still just apply the nth root test and say r is limit n going to infinity of this thing to the 1 over n, which is just simply equal to 1/2. So r is 1/2, and that's between negative 1 and 1. So one way to show that this converges would be to say, well, it converges because 1 over n squared converges and sum of 1 over n squared converges, and if you add 1 over 2 to the n, that also converges. Therefore, the entire thing, when you add them up, it still converges. So that's one way to do it. However, since we just have to show that it converges, it would be nice if we can just work with the entire thing rather than having to work with each individual thing. So my plan is this. I think this will be still a lot bigger than this one because 2 to the n is much, much greater than n squared, right? At least that's true when n is 1 or greater, okay? When there are 2, it's the same. So we know that 1 over n squared minus 2 over n is non-negative. We also know that it's less than 1 over n squared. So therefore, when we have this will be less than sigma n from 1 through infinity of 1 over n squared, and this is finite because of p-test with p equals to 2, greater than 1. Thus, by direct comparison test, it converges. Okay, so this is probably the simplest way to approach this. The more intuitive way would be to show that the summation of this converges and summation of this converges, and then subtract the 2, and you would argue that this converges because of the p-test and this converges because of this. So that would be another way to go about it, but that would require more writing. Okay, what about this one? This one you have 1 over n squared whose summation converges because it's a p-test p-series with 2, p equals to 2, whereas this other one, 1 over n, that diverges. So when you subtract, this is going to be some finite value, whereas this will be infinity. So you're going to end up with some finite minus infinity, which is negative infinity. So that's the intuition we have. This is going to be an infinite value, negative infinite value. So how do we actually argue for that? Well, we want to combine it as a single fraction. Combine 1 over n squared as a single fraction by making common denominators. You multiply n top and bottom, so you get n over n squared, which is going to give you sigma n from 1 through infinity of n squared 1 minus n. Now that's a good thing because that's the dominant term, which is like 1 over n. So if we do a limit comparison test to 1 over n, we will be able to show that it actually diverges. Okay, so now actually this part we don't really need to write on the exam. We start by doing this, and we take the limit n going to infinity of the series we have with the one that we want to compare, and that's going to be limit n going to infinity of n minus n squared over n squared, because this flips over, so it's n over 1, and when n over 1 gets multiplied, n times 1 is n, and n times n is n squared. And now the dominant terms are n squared and n squared, so that gives you negative 1, which is not equal to 0, and sigma n from 1 through infinity of 1 over n diverges, being harmonic series, or you can say p-test, and thus by limit comparison test, this diverges too. Right? Okay, now we have 3 terms, which means you can still solve in the same way. Just put them together. Just slightly less annoying part is that you just get one gigantic product as the common denominator, and then for the first one to have this denominator, you would be multiplying n plus 1 and n plus 2 on the top. And this one you would need n and n plus 2. And the last one you would need n times n plus 1. Now if you simplify this as n squared plus 3n plus 2 minus 2n squared minus 4n plus n squared plus 1 over, this would be n times n squared plus 3n plus 2. And n squared, negative 2n squared, n squared all cancel away. And you end up with negative n plus 3 on top, whereas on the bottom you have n cubed plus 3n squared plus 2n. So this is what you get if you rewrite it. And then, because the dominant term is like n over n cubed is like 1 over n squared. So because you have 1 over n squared, we can do a limit comparison test with 1 over n squared. So let's do that. Lim n going to infinity of negative n plus 3 over n cubed plus 3n squared plus 2n over 1 over n cubed, n squared, sorry. And that's negative n cubed plus 3n squared over n cubed plus 3n squared plus 2n, limit n going to infinity, and that gives you negative 1, which is not equal to 0, and summation of n equals to 1 through infinity, 1 over n squared, converges by p-test. P is equal to 2 greater than 1. Hence series converges by limit comparison test. Now, what's a little bit more interesting is that actually you can find the value of this series, because if you write them out, you'll find that this is a telescoping series. So a lot of things will cancel, and you're going to get a finite value out of it. Okay, so that would be another way of solving this. Okay, we have n factorial over 2 to the e to the n. Since it has a factorial, that means we probably want to do the ratio test. So let's take the ratio of an plus 1 divided by an. And that's this series itself, the sequence copied. And then write down n plus 1 for every n that you see on the top one, e to the n plus 1. Let's simplify, multiply the inside and outside. That gives you limit n going to infinity of e to the n plus 1 factorial, whereas on the bottom you have e to the n plus 1 times n factorial. E to the n and e to the n plus 1, since this is e to the n times e, you're going to reduce these two to get just 1 over e here. Whereas this one, if you write out n plus 1, that's 1 times 2 times 3 all the way up till n plus 1. And this is all the way up till n. So a lot of these will cancel, leaving just n plus 1 on the top. And then you're still sending n to infinity, which will make this thing infinity. So what you're getting is 1 over e times infinity, which is just infinity. Okay, so what does that mean? Since infinity is bigger than 1, by ratio test, series diverges. Okay. Now this one will be the opposite. If you do r equals to limit e to the n factorial down here, and e to the n plus 1 over n plus 1 factorial down here, because this is just the reciprocal of the previous one, if you simplify this, you're just going to be getting the exact same thing as what we had before here, which was n plus 1 over e, except that since it's the reciprocal, you're going to get instead e over n plus 1. See, the previous one, this one had n plus 1 over e, and now we have e to the n plus 1. If you take some time to cancel everything, you're going to see that this is what you get, which is 0, and since 0 is between 1 and negative 1, it converges by ratio test. Okay, this one, if you have something times some power, we saw an example like this before just now, and we did both root test and ratio test, and it turned out that ratio test was slightly easier. So let's just use ratio test, but you can use root test if you want. So infinity ratio means copy it down here and then copy again, but every n should be replaced by n plus 1. And that's n plus 1 over n times, this will have an extra 1 over 6 there, limit n going to infinity, and because this just gives you 1, see, dominating terms are n and n over n is 1, so that's just going to be 1 times 1 over 6, which is 1 over 6, and since 1 over 6 is between 1 and negative 1, converges by ratio test. Okay, what about tangent? Well, the tangent also have a similar property as the sine. See, tangent, we know this is like tangent x is sine x over cosine. And if you recall sine x, I said this is like x minus 1/3, 1 over 3 factorial x cubed, and so on and so on. And cosine is like 1 minus 1 over 2 x squared, 1 over 2 factorial x squared, then plus so and so. So when x is really, really small, sine x is like x, and cosine x is like 1. So this one, when x is really small, it will be like x over 1. So that's why when you have a limit like this, you'll be getting, you're going to get the tangent of 1 over n squared plus 1 would be very similar to 1 over n squared plus 1 itself. And because 1 over n squared plus 1 is again very similar to, so what I'm trying to say is that tangent of 1 over n squared plus 1, when n is really large, then let me erase this just for a minute. If n is really large, then 1 over n squared plus 1 will be very, very small. So it'll be like just x over 1, which means it's like very similar to 1 over n squared plus 1. And then since this is very similar to 1 over n squared, and we know that sum of 1 over n squared converges, we will know that tangent of this one, when you add them up, it will converge. If you are not so sure what I just said, just try to compute tangent of 1 over, say, 100 squared plus 1, and compare that value with 1 over 100 squared plus 1. If you put both of these in Google or something, you're going to see that these two values are very, very similar to each other. Okay, so this portion was just to gain some insight into the problem. You don't really write anything like this on your solutions. It just helps you to determine what you want to compare with. So by this thought process, we decided that tangent of 1 over n squared plus 1 is very similar to 1 over n squared. So these two are comparable. And once we determine that these are comparable, then we can then go ahead and use the limit comparison test. Okay, so let's apply the limit comparison test. Limit n going to infinity of tangent of 1 over n squared plus 1 over 1 over n squared. Okay. Now I see that they both have n squared here, right? So let's just define u to be equals to n squared to simplify a little bit. So this is like 1 over n squared, dividing by 1 over n squared is multiplication by n squared over 1 times tangent of 1 over n squared plus 1. But then both of these n squared, I'm going to change it as limit u going to infinity of u times tangent of 1 over u plus 1. Substitution is very, very powerful when solving limit questions. So if you see some way to simplify your question by using substitution, always do so. Alright, now I don't like this that much because you have this 1 over u plus 1 inside tangent. I guess I can still manage to make x as 1 over u plus 1 to do some substitution. If this is true, then if I multiply u plus 1 both sides, then u plus 1 times x is equal to 1. And when you divide by x, u plus 1 is 1 over x. Subtracting 1, it will give you u equals to 1 over x minus 1. So what you get, and I really want this to be like 1 minus x over x. Okay. So when you get u going to infinity, actually when u is going to infinity, then x is going to 0, right? So when x is sent to 0 plus, u can be written as 1 minus x over x and times tangent of x. Okay, this is wonderful because now when you plug in 0, tangent of 0 is 0. When you plug 0 in the denominator, that's also 0. So this is 0 over 0 type, which means you can use the L'Hopital's. So we're going to do the L'Hopital. We'll differentiate the top, which is by the product rule, it gives you negative tangent of x. And then when you differentiate tangent, that's secant squared. So it's plus 1 minus x secant squared of x. Over, when you differentiate x, it's just 1, and you're sending x to 0, plus. Now when you plug in 0 here, tangent 0 is 0, secant 0, well, secant is 1 over cosine, and cosine 0 is 1, so this will be like 1 over 1 squared, which is still 1. So when you plug in 0, you're going to end up with 1 minus 0 times 1 squared, which will be 1. And that's not equal to 0, and that's what's important. And since sigma n equals to 1 through infinity of 1 over n squared converges by p-test, p is equals to 2 greater than 1, series converges by limit comparison test. Okay. Alright, the next question, this one, it's kind of tempting to use the root test because everything has nth power, but the problem is if you have 3 to the n plus 2 to the n and you take 1 over n, unfortunately, because this is not a multiplication, you can't distribute 1 over n to each one of them, so that doesn't work. So that means that you want to use ratio test or maybe some other test. But before you do that, let's think a little bit more. What is which one is much bigger, 3 to the n or 2 to the n? Well, 3 to the 4th is 81 and 2 to the 4th is only 16. 3 to the 5th is 243, whereas 2 to the 5th will be 32. So you see that this is going to be much, much bigger. It will grow much faster than 2 to the n. So what I'm trying to say is that this is going to be the dominating term. And therefore, when you have 3 to the n plus 2 to the n, this is going to be dominating when n is large. So you're going to get something similar to 3 to the n over 7 to the n. But that's 3 over 7 to the nth power, and that definitely converges because this is a geometric series with r equals to 3 over 7. And that means it's a good idea to do a comparison, a limit comparison with this series. Okay, so that's where the idea comes. Alright, so let's do the limit comparison test. We're going to take what we're given, divide it by 3 to the n over 7 to the n, which is like 3 to the n times 7 to the n in the denominator, whereas on the top 3 to the n plus 2 to the n times 7 to the n. And as you can see, the 7 to the n cancels away, and you get 3 to the n over 3 to the n is 1. 2 to the n over 3 to the n is 2 over 3 to the n. And you're sending n to infinity, therefore that's going to be 1. Because this is less than 1, so if you multiply 2/3 again and again, you're going to get 0. So this will be like 0 and you get 1, which is not equal to 0. And we also know that sigma, n from 1 through infinity, of 3 over 7 to the nth power is a geometric series with r equals to 3 over 7, which converges by because r is between these two values. Okay, and then thus series converges by limit comparison test. All right. Oh, we have a factorial. Let's just use the ratio test. Copy that thing down here, and then you rewrite it with n replaced by n plus 1. So it'll be 3 n plus 1, and going to infinity, and then it'll be n plus 1 factorial times the e to the 3n, and these two multiplies that they're going to go down here, and I expanded 3. I distributed the 3. 3 times n is 3n, 3 times 1 is 3. Limit n going to infinity. This one here is really e to the 3n times the e to the 3, so these two will cancel away. N plus 1 factorial over n factorial. We've seen this too many times, right? This always gives you n plus 1. So you're going to end up with n plus 1 on the top and e cubed on the bottom. And you're sending n to infinity, which is like infinity over e cubed, which is infinity. Okay, so what do we know about this? Since infinity is bigger than 1, by ratio test, series diverges. Okay, let's think about this one. Sine of n, that's always a problem. Sine of n or cosine of n, these trig functions, sine n or cosine n. All you know about these is that it gives you some value between 1 and -1. So we should try to see what happens to these two series. Okay. But then when you look at this, you realize that sometimes sine of n is negative. See, sine is a graph that goes like this, so sometimes it's positive, sometimes negative. So you don't know when it's going to be positive or negative. So this is not always a positive series. It's sometimes negative, sometimes positive. So that means it'll be hard for us to use the direct comparison test, because direct comparison test requires the series to be positive. Another consideration is, what if we try the limit comparison test? Well, that's hard because sine of n, it's hard to do much about it. So when you have sine of n like this, it's really hard to use limit comparison test. It's not going to be really helpful. Alright, so what do? Well, we first look at this and say, oh, since the signs are sometimes negative, let's see if it's absolutely convergent. Actually, that's the key. You want to show that it's absolutely convergent. Now, this one is always less than 1 over n radical n, because sine of n absolute value is less than 1, right? But what is this? This is sigma n from 1 through infinity, and then 1 over, this is n to the first power and n to the 1/2 power, so 1 plus 1/2 gives you 3 over 2. So this one converges by p-test with p equals to 3 over 2, which is greater than 1, right? And therefore, since this series is bounded above by a finite number, and you're adding some positive things, this has to converge because it cannot grow to infinity. So our conclusion is that sigma n from 1 through infinity sine n over n times radical n absolute value converges by direct comparison test. Now, what does that mean for the original series without the absolute value? It means that this converges also, and because it converges absolutely. Okay, so this series actually converges absolutely. Alright, L. What do we have here? Remember that sine of x is very similar to x when x is very small. For small x. It's nice to check that this is true, because try like sine of 0.123, and you're going to get a value very similar to 0.123, slightly lower. Okay, well, anyways, it's indeed true that sine of x is similar to x. And because of that, n times sine of 1 over n cubed, when n is a large number, this will be very similar to n times 1 over n cubed, which will be like 1 over n squared. Okay, so we kind of see that this will be like 1 over n squared when n is really large, which means that summation of this will be behaving similar to summation of this, which converges because it's a p-test, right? So we do all this work and not put that on the solution. We don't need to. We can put it, but it's not really needed. So now here's the actual solution. We first discussed that sigma 1 over n squared n from 1 through infinity converges by p-test, where p is equals to 2 greater than 1. And then we say limit of n going to infinity. We're going to do the limit comparison test. N times sine 1 over n cubed, that's divided by 1 over n squared. And then, since this is okay, well, you can just now show that this is 0 over 0 and do differentiation. You do the L'Hopital's, differentiate the top and bottom to get the limit. But I mean, whenever whenever you have something that's complicated as a limit, try to see if you can do any kind of substitution. That really helps. Okay, so we're going to say 1 over n cubed is equal to x, so that I end up with sine of x. Yeah, that really helps. So that means n cubed times x is 1, and n is equal to, n cubed is equal to 1 over x, 1 over x. So n is like 1 over x to the 1/3 power. Okay, so let's see, or you can say 1 over x to the 1/3 power. Okay, so let's see, what do we have? We have limit, when n goes to infinity, x is 1 over infinity, so x goes to 0 plus. N is 1 over x to the 1/3 power. Sine of x. See, if you are to differentiate later, it's always a good idea to have the inside function to be simplified. That's why I took x as 1 over n cubed, not x as 1 over n squared. It's always beneficial to have sine of x, right? Okay, and then this one is 1 over x to the 1/3 squared. Sorry, 1. And that means if you simplify this by, well, let's see, this will be actually 2/3, right? So, oh, this is confusing. First, you have, right. So this over this will be flipped over, so you're going to get 1 over x to the 1/3 power times sine of x times 1 over x to the 2/3 power. And that's nice because x 1/3 times x to the 2/3, that's just x. Right? So you have limit x going to 0 plus, and we all know that that goes to 1. If you didn't know that, you can still use L'Hopital's to show that it's 1. But that's not equal to 0, so by limit comparison test, series converges, because we compared it with the converging series. Alright, now we do m here. Log of n over n. Well, see, log of n over n, that's bigger than 1 over n, except when n is 1. When n is 1, log of 1 is 0. So starting from n, I guess from 3 and afterwards, this is true because log of 2 is still less than 1. But the reason I say this is because I know that this diverges. So if you have sigma and sigma, since this diverges, this is going to diverge too. So that's how you would argue. So that will be one way to do it. See, you have, so we're going to do direct comparison test, and since ln of n is greater or equal to 1 if n is greater than 3. Actually, this is just not on the solution. The actual solution starts here. Okay. Right, so if n is 3 or greater, log of 3 is 1 point something something. So it's greater, and afterwards is always greater. So we know that ln of n over n is greater or equal to 1 over n. Just by dividing both sides by n. So you divide left side by n, the right side by n, we get this. Now what do we get? That means if we do n equals to 3 to infinity of ln of over n, that should be greater or equal to sigma n equals to 3 to infinity 1 over n. I'm starting from 3 because this is only true after 3. But this is a harmonic series which diverges because it's a harmonic series. And then if it's a harmonic series and it diverges, since this one's bigger than infinity, so this goes to infinity, since this is bigger than infinity, by direct comparison test, this diverges. Okay, so this is how you can do it. So that's just one way. Now, what's another way to do it? Well, we don't really have much options for dealing with this because pretty much this is not any kind of p-series. If you use ratio test or root test, it's not going to give you anything definite. So ratio test or root test applied to this will give you just 1, which means you can't use that test. So the only other one that you can actually use to prove that this diverges is actually the use of the integral test. So you can do an integral test 1 through infinity log of x over x dx, and this is, if you set u equal to log of x, then du is like 1 over x dx. So dx is equal to u times x times du. So you're going to get 0, log of 1 is 0, so it starts from 0 to infinity, of u over x times dx is x times du. So these cancel and you end up with u du, which is 1/2 u squared, and you plug in infinity and 0, you get infinity. So once you get this, you can say by integral test diverges. Okay, so that's another way to do it. But you know, integral test is used very infrequently. Rarely you have something that's easy to integrate like this. So this is more like an exception to the rule. Okay, so but for this problem, I think integral test makes more sense. Okay, this one here, this is similar to another question that we did before. We had 3 to the n, 2 to the n, 7 to the n just now, right? And over there we were saying that this is a dominant term, so when n is really large, it's like 3 over 5 to the nth power, and this is like a geometric series with r equals to 3 over 5. So that's going to diverge, no, converge. This will be converging because 3 over 5 is between -1 and 1. So that's it. This is what we're going to compare with. So we're going to say limit comparison test, limit n going to infinity of our given series divided by this thing that we're comparing with. This is the same as 3 to the n over 5 to the n. If you flip this over, that's same as 3 to the n plus 2 to the n over 5 to the n minus 2, and you're multiplying it by 5 to the n over 3 to the n, limit n going to infinity. And then if you divide this by this, you get 1 plus 2 over 3 to the n. Okay. So this over this is same as that much. That means we're left with 5 to the n over 5 to the n minus 2. But that one we are also going to divide by 5 to the nth power, so that you get 1 on top. 5 to the n divided by 5 to the n is 1. And then you have 2 divided by 5 to the n. And that's the trick of solving this limit. If you do this, then this goes to 0, because if you multiply 2/3 over and over again, is 0. And 2 divided by 5 to the n, which is infinity, will also be 0. So you're going to end up with 1 times 1, which is 0. And then we say, since sigma of 3 over 5 to the n, and from 1 through infinity, is a geometric series with r equals to 3 over 5, it is convergent, because r is between -1 and 1. Thus, by limit comparison test, the sigma n from 1 through infinity, 3 to the n plus 2 to the n, 5 to the n minus 2 converges. Okay, so that's our answer. Okay, now we see here it's a alternating series, and if you actually take the absolute value, This is actually the previous question that we solved. This one we saw that this diverges. Okay. And therefore this sigma n from 1 through infinity with negative 1 to the n ln of n over n does not converge absolutely. Okay. So if it does not converge absolutely, we should apply the alternating series test to see if it does converge conditionally. So we need to apply alternating series test. First, we have to see if the limit n going to infinity of ln n over n is 0, but this is infinity over infinity type, so we can differentiate the top, which is 1 over n, differentiate the bottom, which is 1. When you send n to infinity, that's 1 over infinity, which is 0. So it does satisfy the first condition of the alternating series test. Second is we have to show that ln of n over n is a decreasing series, and I said when both top and bottom are increasing, and it's hard to see what's increasing, what's decreasing. To show that the entire thing decreases, it's a good idea to just differentiate it and show that it's negative. So we apply the quotient rule here. Differentiating ln of n gives you 1 over n times the bottom, which is n, minus differentiate n, and then derivative ln of n is not differentiated, and you have denominator squared, which is 1 minus ln of n squared, and that's actually less than 0 for n 2 or greater, right? So eventually it does decrease, and therefore by alternating series test, so this one means that an decreases. Okay. Both conditions of the AST is met, and thus by AST this series converges conditionally. Okay, we have something with n power, so that would mean that we need to use the nth root test, the root test, which is to take 1 over nth power. Since these two multiply, we end up with 2n on top, n minus 2 over n at the bottom. And for these, the kind of change of substitution that worked was to set x as 1 over n. So the n is equal to 1 over x. And then that will give you limit x going to 0 plus n is 1 over x minus 2 over 1 over x, 2 times 1 over x, which is equal to limit x going to 0 plus, well, this 1 over x flips over to give you x over 1. When x over 1, which is just x gets multiplied to 1 over x, it's 1, whereas x gets multiplied to 2, that's 2x. And it's 2 over x that's multiplied. Now we are ready to do the e to the ln trick. So we rewrite this as e to the ln of 1 minus, 1 minus 2x to 2 over x, and 2 over x jumps over the log, which gives me limit x going to 0 plus of e to the 2 over x, 2 times ln of 1 minus 2x over x. And now, because this is, when you plug in 0, it's ln of 1 over 0. ln of 1 is 0, so this is really 0 over 0 type, which means I can use the L'Hopital's. So apply the L'Hopital's, the derivative will be negative 2 over 1 minus 2x by the chain rule. Derivative of x is just 1. When you plug in 0, you end up with e to the negative 4. And that's actually less than 1, and that's actually bigger than negative 1. So by root test, series converges. Okay, Q, last question from this set. We have 2 to the n, square root of n, 5 to the n. This one, let's see. I guess you can use either the ratio test or root test for this. Let me show you how to do the ratio test. Limit n going to infinity. It's the series itself copied in the denominator. And then you put one more, n plus 1, square root of n plus 1. And then 5 to the n plus 1. If you simplify this, 5 to the n plus 1, 2 to the n square root of n here, and then 5 to the n times 2 to the n plus 1, square root of n plus 1. Then 5 to the n, 5 to the n will cancel, leaving 1, 5 down here. 2 to the n, 2 to the n will cancel, leaving 2, one of the 2 on the top. And you're going to get square root of n plus 1 over square root of n. But that's just limit n going to infinity of 2 over 5 square root of n plus 1 over n, which just goes to 1. So that's just 2 over 5 times square root of 1, which is just 2 over 5. Since 2 over 5 is between negative 1 and 1, by ratio test, series converges.